Hey, welcome back. So as you know, I've been trying to train my own large language model from scratch, and today I'm finally going to start to show you how I've been doing that. But before we can get on to training a model, we actually really need to understand how a large language model works. So today I'm going to present a really simplified reference model that I've been using to describe a large language model. And then as the videos go on, we are going to delve into each layer. So by the end of this, you should really be able to understand how an LLM works. And when you start reading things like papers, you'll understand what the terms are, and actually you'll be able to build your own model. Now, you're probably thinking to yourself, actually, I'm never going to build my own model, but maybe one day you might decide to fine tune a model, and therefore having this deep understanding of how the models work is really going to help you. But actually, just interacting with AI and large language models, having this knowledge is super, super important. So to get started today, I'm going to present that reference model. We're going to have a little bit of a play with the HuggingFace transformer library. We're going to look at things like model configuration, and we're going to look at things like model architecture at a high level, but enough to get you familiar and interacting with it. And then maybe at the end, we're going to have a little bit of fun with tokenizers, and we're going to see what happens if I take a tokenizer from something like Llama and then apply it to Mistral, just for a little bit of fun. So before we start looking at that reference model, what we're going to do is use the transformers library from Hugging Face just to load and run a model. Nothing more than that, and then we'll start to break down a little bit what's going on. So we are going to use Google Colab, so you can go to colab.research.google.com. And then all you will need to do is click on New Notebook. Now, don't worry about it. They give you a free tier, so you can do some computer on that for free. So to get started, I'm just going to paste in this piece of code, which allows us to use the Hugging Face Transformers library. And specifically, the model I'm going to use is the TInyLlama model. It's a 1 billion parameter model, and it's an open source model, but it's small enough to run in the free tier of Google Colab, and we can do a lot of fun and experimentation with it, and it's a very, very powerful model. So in this case, we're going to get the tokenizer from the model. I'm going to explain what that does a little bit later on. And then we're going to load the model. Again, we're going to deep dive into how that works a little bit later on. And then we are going to then create a pipeline for the text generation, passing in the tokenizer in the model. And then we're going to ask it the question, who is Ada Lovelace? And then the model is going to come back with an answer, and we're going to print that out. To make that run, I am just going to select my runtime type. In this case, CPU is probably enough. I'm going to set it to high RAM, but I don't think we actually need that in this case. But when we're using other models like Mistral, for example, then you may need a high RAM model. But once that's working, I'm just going to click connect, and then that is going to create me a Google Colab runtime on the back end. Now, if I just hit play here for a second, then it's going to walk through this code. The first thing it's going to do is download the tokenizer, then it's going to download the model. The model's quite big, it's a couple of gigabytes, so it'll take a few seconds to get that downloaded, and then once it's downloaded, it will be able to do the inference. And as you can see, it's came back with who is Ada Lovelace, and then it says Ada Lovelace was a mathematician and writer who made a significant contribution to the field of computer science. She's the daughter of Charles Babbage, so that's completely wrong. She's not the daughter of Charles Babbage. She worked with Charles Babbage. She was actually the daughter of Lord Byron. But that's beside the point. You can see it's coming back with a reasonably intelligent looking answer, albeit wrong. So now that we've been able to load and interact with the model, let's break down what this reference model looks like. So at the very bottom there, you can see this question, who is Ada Lovelace? That was the question we asked. This is our input text. And then at the top there, you see the output text is Ada Lovelace is the daughter of blah, blah, blah. And that is the final result. Now, the first thing that I want to say here is those two layers, the input text and the output text, is never seen by the model. The model knows nothing of those words. It deals with the idea of embedding. So it's actually looking at a tokenized representation of those words. So everything that the model deals with is essentially numbers, and it has a vocabulary. So to be able to ask the question of who Ada Lovelace is, we actually need to take that question and tokenize it, i.e. convert it to a number form first. And then we would pass in those numbers into this embeddings layer in the LLM, which we'll come back to in a second. And then eventually, once the LLM has processed this, it is going to return its output as tokens, and you can see that in the tokenized output layer. So 23255 is the token for Ada, and then we would run it back through the tokenizer again, and then that is going to output the Ada Lovelace is parts, translate it from its tokenized form back to English. So if we come back to our original code and look at the imports, you can see from transformers import AutoTokenizer, and then you see our model name is TInyLlama, and then we've got this piece of code here, which is tokenizer equals AutoTokenizer from pre-trained model name. That is actually retrieving the tokenizer from HuggingFace, and that is what is responsible for doing the tokenization. So underneath the hood here in pipeline, it is actually going to take that phrase who is Ada Lovelace and do the encoding into its tokenized form, and when it gets a result, it's going to do the decoding without us seeing that encoding and decoding process. And if I wanted to, we could actually do that for ourselves. So if I typed in here from transformers import AutoTokenizer, and we will just break this down as we go along. And then we put back in the model name as TInyLlama1B chat. Again, we'll look at that model in HuggingFace in a few minutes. And then if I set tokenizer is equal to AutoTokenizer dot from underscore pre-trained, and then I pass in the model name, and then I print out the tokenizer. If I now run that, you can see it's going to come back as saying it's using the Llama tokenizer fast. It's associated with the model TInyLlama. That's where it's pulled it from. It's got a vocab size of 32,000. We'll talk about that in a second. And then it's obviously a fast tokenizer. What do we mean by a fast tokenizer? It's really simple. A fast tokenizer is a tokenizer that is written in Rust. If isFast is equal to false, then it's just a standard Python tokenizer. That's all it means. So underneath the hood, somebody's written a Rust tokenizer, so it runs a little bit faster. Now, there's a lot of details about this tokenizer here, about the padding and truncation, special tokens, beginning of sequence tokens, end of sequence tokens, unknown tokens, padding tokens. Again, we will go through this in a later video, but this just allows you to see that if you want to get into more details of what the tokenizer is, then you're going to be able to do that. Now, if you're thinking to yourself, hang on, how does the AutoTokenizer know which tokenizer to use for this model? Well, I'm going to show you. If you go to HTTPS and you go to huggingface.co, and then you just paste in the name of the model, TInyLlama, TInyLlama1B chat, you are going to end up in the Hugging Face page. Now, Hugging Face is really just like a kind of GitHub repository for large language models. So you can go and explore that, and you can find lots and lots of other models in there, whether it's MetaLlama or Falcon or whatever. But today we're looking at TInyLlama. And then if I just click on files for a second, you can see a whole load of different files there. But as you can see here, there's a file called tokenizerconfig.json. If we select this, you can see add tokens decoder, BOS token, end of sequence token, etc. And if we come back to our Google Colab, you can see it's the same data that is being displayed there. So it doesn't take a genius to realize what is actually happening underneath the hood is it's just reading this config file from Hugging Face. So it's just essentially downloading it and reading it. What is actually particularly cool here, there is actually more data available here. So you can see the tokenizer model. So actually the model they use to train the tokenizer has actually been uploaded by TInyLlama. So that's very cool. And then tokenizer JSON is actually the dictionary file for the token as well. So if you want to see how everything is mapped together, you can download that tokenizer JSON and look at it. If I wanted to, I could actually encode the prompt myself. So I could just type in prompt equals who is Ada Lovelace, which was exactly the question we asked a second ago. And then I'm just going to have a new variable called encoded prompt, and then I'm going to call tokenizer.encode, and now I'll just pass in the prompt that I want to encode. And then of course I can even print it out, so we'll print out the prompt and the encoded version. And again, you see who is Ada Lovelace, and it comes back with 116433382325. And if I come back into my reference model for a second, you can see 11664433382325. And as you can see, it exactly represents the numbers in the reference model. If you're curious, 1 stands for beginning of sequence, 11644 is who, 338 is, and then 23255 is Ada, and then so on so forth. So that represents our tokenized form. But if I come back into my original inference code, that is happening underneath the hood within that pipeline function. If I really wanted to, if we wanted to see the exact encoding, we could just do a for loop over the encoded prompt, and then I could call the tokenizer decode, and then that will give me the decoded version, and then I could just print that out. So if we run that for a second, you can see exactly as I said. 1 is the beginning of sequence, who is Ada, and then 23974 is the LOV, and then EL is 295, and then ACE, and then the question mark is 29973. As you can see there, it obviously doesn't have the word Lovelace in its vocabulary because it's not a frequently used word. So it's actually using subwords to make up the entire word Lovelace. In this case is LOV, EL, ACE, there. So 3 tokens are making up the word Lovelace. And that's again due to the restricted vocabulary size. In this case, the Llama tokenizer has 32,000 tokens in its dictionary, and Lovelace isn't one of them. And this is the idea of subword tokenization, to be able to keep your vocabulary size short. And again, in the next video, I'm going to explain exactly why you want to have vocabulary sizes short and how that affects things like the embeddings layer in our reference model. And again, that decode process that we were showing you there, that actually happens underneath the hood in that pipeline. Again, it's not part of the model, but it is happening in that pipeline function. So if I come back into this reference model for a second, you can see we've now covered who is Ada Lovelace, and we've covered the tokenization input, and we've covered the tokenization output, and the output text Ada Lovelace is. That is all happening by the tokenizer. It is not happening in the large language model. Now, because the tokenizer JSON is actually the thing that the AutoTokenizer is using, then if you don't know what tokenizer is being used by a model, you could just go and look up in HuggingFace that particular model and then go and see which tokenizer is being used. And in fact, it's the tokenizer class that is the specific attribute that tells you which tokenizer. So in this case, it's using Llama tokenizer. If I want to, I could get rid of the AutoTokenizer and I could paste in Llama tokenizer, and then I could paste Llama tokenizer here, and now run that again, and then you see it's going to continue to work. You see it's using Llama tokenizer. Again, in this particular case, it's saying is fast is equal to false because I've used the standard Llama tokenizer in this case, so it's going to be using the Python implementation. But similarly, if I wanted to, because it supports fast, I could just put fast here, and then I could replace this with fast here as well, run that again, and now I'm using Llama tokenizer fast, and you see the is fast is equal to true. So the AutoTokenizer is just using this tokenizer config to be able to figure out which tokenizer it's using. It's, funnily enough, the model itself has no clue about the tokenizers. It is completely abstracted from the model. It just knows it's about its vocabulary, which is held in the embeddings layer. And again, I'll cover that in the next video. Now, to prove this works really well, if I wanted to, I can actually put in a completely different model name. So in this case, I'm going to use the very popular Mistral 7B model. So we're going to put in Mistral AI / Mistral 7B, and we are going to take version 0.1. Again, similarly, you can take this, go into Hugging Face, replace this piece here, and then you can actually look it up, click on Files and Versions, and then, as I said before, you've got this tokenizer config here. So as you can see here, it's actually using a Llama tokenizer as well, which is really cool. So Mistral has reused the Llama tokenizer, but interestingly enough, its actual dictionary is completely different. So although it's using the same tokenizer model architecture, it's actually got a completely different dictionary. So different things map to different numbers. And we can prove this as well. So if I now run this, and you can see that I'm not using the AutoTokenizer, I'm using Llama Tokenizer Fast in these cases. But instead of using TInyLlama, I'm using Mistral 7B as the model name. And this continues to work. So it's come back, who is Ada Lovelace? It's came back with an encoding, so you see who is Ada Lovelace. But these numbers here are completely different from the Llama tokenizer. So it's using the same tokenizer architecture. So it's reusing the Llama tokenizer, but it's actually got a different dictionary. So the numbers map to different tokens. So if I want to do something completely bonkers, because Mistral uses the Llama tokenizer, I could, if I want to, use the Llama tokenizer with the Llama model, the TInyLlama model, and then pass that into Mistral AI for tokenization. It will generate complete gibberish, but because they're compatible architectures, this would work. So to prove that, I'm going to pull in Mistral AI Mistral 7B version 1. I'm going to change this to tokenizer model name. So rather than using Mistral AI as my tokenizer, which is the sensible thing to do, I can actually pass in the tokenizer model as TInyLlama. So I could use the TInyLlama tokenizer, but use Mistral AI as the model. And then if I run that, I'm going to ask the same question, who is Ada Lovelace? This will work, but it's going to come back with complete gibberish because who is Ada Lovelace, as you remember, actually maps to completely different numbers from what it's expecting. So rather than having 11644 for who and 338 for is, it's actually going to get 6526 for who and 349 as is. Now in this case, I have no idea what they are mapping to in the Mistral version of the Llama tokenizer and its dictionary, but either way it's going to come back with complete gibberish. But it will work because it's got the same embeddings dictionary. It's a 32,000 size dictionary with the same size of dimensions. So we have compatibility on the embeddings layer. It just happens to be that we're passing through gibberish. And there you go. As you can see, it's came back. I mean, it's complete gibberish it's came back with, but you know, it certainly has actually came back and made a prediction. If I want to, of course, if I want to get a sensible output from Mistral AI, I can just replace the tokenizer model name back with Mistral AI 7B and then run this again, and then it will come back with a sensible answer. And I think this is quite important because as we start to build our own large language model, there actually becomes a decision point, which is, do I want to use an existing large language model architecture? So in the case of Mistral, they decided to reuse the Llama architecture, but they made a decision to have a different token dictionary from Llama. So, you know, and you can understand that because you're going to have different influences as you build these models. You may want it to handle different languages, maybe something like Rust or C# differently from how another model does, but you want to reuse the architecture, i.e. you don't want to rebuild your own tokenizer, which is a lot of effort. So again, that's a sort of decision point you make as you build these models. So in the case of Mistral, they decided to reuse the Llama tokenizer, but obviously have their own dictionary. In the case of TInyLlama, they chose to use both the tokenizer and the tokenizer dictionary, so it has full compatibility with Llama. And that opens up interesting scenarios for the future if you want to do some things like merging and transfer. Again, we'll cover that in another video. And I think there is some other advantages to reusing an existing tokenizer without the need to actually having... And I think there are some other advantages to reusing an existing tokenizer. So actually, if you look at what went on with Mistral, even just this weekend, there was a leak of an older Mistral model, and that model, which was, I think it was a 70 billion parameter model, they actually took the existing Llama 2 70B model and then they fine-tuned it with their data whilst they were doing the pre-train of their base model. And then, of course, once they got their pre-train worked, then they plonked their data they used for the fine-tuning on top to create their own model. Now, that's an interesting approach because it means that you can go pretty far with fine-tuning, and then as you build your own pre-trained model in the background, you can kind of replace that. And again, you're going to have more consistency if you're using the same tokenizer, etc. in the architecture. So I think that was an interesting approach. And that may be an approach that we take as we build our large language model, that we use a fine-tuned version of an existing model whilst we train our own base model in the background. As you can see now, it's came back with a response. I'm now using the Mistral's tokenizer token dictionary. I'm using the Mistral model itself, and you can see now when I ask the question, who is Ada Lovelace, it comes back with a sensible answer. So I think we've covered tokenization quite well at a high level, but now I want to get you a little bit familiar with model configuration and model architecture. So if you want to discover what the model configuration is for your model, again, you can actually use the transformers library to help you again. So if I do from transformers import autoconfig, and then I set my model name, and we'll use TInyLlama again, just because it's a smaller model and it's easier to work with. So I'll set my model name equals TInyLlama, and then I'm going to say config is equal to autoconfig, and we'll do from underscore pre-trained, and then I will pass in the model name as we did before, and then I will print out the config. And if I just run that for a second, you can see it's came back fairly quickly, and it's saying llama config. You see it's TInyLlama. The architecture is llama for causal LM. We'll talk about that in a second. And then you can see it's coming back with what the beginning of sequence token ID is. So in this case, it's 1. Remember when we did the infer earlier, you see that number 1 there, and then forward, the S tag there, that's the beginning of sequence. You see that's actually called out in the model config. And again, there's an end of sequence token, which is token 2. It's not coming back in that particular case. There's a whole set of other things that we're going to get into in other videos, but we're not going to focus on that too much today. But as we go through each of these videos, we will start to go into these things in more detail. The thing I want to point out, though, is what you can see here is vocab size is 32,000. That, in that particular case, is actually the embeddings layer we were talking about, the vocab length. So the tokenizer supports 32,000 tokens in both the Llama tokenizer case, whether it's Mistral or whether it's TInyLlama or Llama-2, and that is kind of where that is pushed in. And again, we'll go into more details about embeddings in another video. But you can access the config, and of course, if you are curious about where the config comes from, we just go back into the file section here, and then if you look at the config JSON for TInyLlama, you can see architecturals llama for causal LM, and then there's all the information that I just showed you over here. So it's really just reading that llama config file from the HuggingFace repository. And then, of course, if I wanted to, I could go to something like Mistral, look at the 7B model, and then, of course, if I go into files and we click on the config JSON there, for example, you can see there is the architecture, in this case, Mistral for causal LM. You can see it's got the same vocab size. That is why I was able to do that trick of putting in the TInyLlama vocab into the Mistral model, and it worked, even though it generated gibberish. Again, whole other things there, similar beginning of sequence tokens, end of sequence tokens. Again, we'll go into all of the other stuff in later videos, but you can explore that. And of course, if I wanted to, I could just change the model name to Mistral here, and then it's going to come back and show Mistral's details. But let's just set that back to TInyLlama so that we can see Llama's details. Now, one of the things I want you to notice here is Llama for causal LM. Again, if you're wondering what a causal LM is, it actually just stands for causal language model. And if you're wondering what a causal language model is, it just basically means a model that does next token prediction. So in the case of all large language models, they are actually next token prediction models. So when I type in something like who is Ada Lovelace, it's predicting the next token is going to be Ada, and then it is going to look at who is Ada Lovelace question mark, and now Ada, and then the next token it's going to predict is, and then so on and so forth. Eventually you're going to get to the kind of full answer, but it's just predicting next token over and over again. And that's what it means by causal LM. It is a next token prediction model. And if I want to delve in particular into the architecture, not just the config of the model, I can actually do a from transformers, and we'll do an import auto model for causal LM. So we're going to look at, so we're again, I think you're probably working out what's going on. Auto model for causal LM is really just going to go and look up HuggingFace and then find the kind of model architecture. We'll put the model name as TInyLlama, and then we'll do a model equals auto model for causal LM dot from pre-trained, and we'll pass in the model name, and of course I can print out the model. And as you can see, it's came back with the model architecture, and you can see it's of type llama for causal LM. So you're probably working this out for a second. If I change this from auto model for causal LM and just put in llama for causal LM, which is the same one that's came back from the config here, and then I replace this little auto model with llama for causal LM, run this again, you're going to see it's going to come back with the exact same answer. So the auto model, if you think about what's going on, it's just looking up in the config.json, figuring out what the architecture is, in this case llama for causal LM, and then it's using that to then load up the model, and that's really about it. That's all the auto model is doing, but of course I'm just short-circuiting it because I know what the architecture is, so I'm just putting llama for causal LM, and then off we go. And now it's coming back with a response. You're seeing it's a llama model. Here's the embeddings layer that I keep talking about, which is the kind of where the vocabulary is listed. In my next video, I'm going to cover that as well. And then in my reference model, here is all of these attention layers. So you see the kind of llama decoder layers. In this case, it's the transformer layers in this case, and then there's an output layer at the bottom. So if I come back into my reference model for a second, you can start to see here that the output layer was that sort of output that I showed you before. The attention layers was those sort of 22 layers of transformers or whatever it was in TInyLlama, and then that embeddings layer of 32,000. So that is what the large language model is. So if you want to go and look at any of those open source models, you can, that are in HuggingFace, you can just go and literally inspect the architecture and the config using those commands. And it doesn't matter which one you use. You can do this for Mistral, you can do it for Llama, you can do it for Falcon, or TInyLlama or Pythia. You can just choose whichever ones you want. And now finally, if I come back into my inference code for a second, I'm hoping you're starting to see that if we look at this code here, we've pretty much explained everything apart from pipeline, right? Which is, you know, if we come back here, we've set our model name. The tokenizer is loading the tokenizer from the HuggingFace directory. The auto model for causal LM is, again, is just looking up the model in HuggingFace, getting its config, reading through that, and then loading the model. In fact, if we look in here again, the actual model itself, all of the weights, etc., we'll talk about that in another video, is actually in here. So you see model, safe tensors, etc., 9.94 gig, 4.54 gig. This is for Mistral. You know, that's actually what it's downloading. That's what it's loading the model for. So it's all stored up in HuggingFace. So It's then going to go and load that, and then we pass in what the model we're using, what the tokenizer is, and then underneath the hood, the pipeline's doing all the encoding, decoding underneath the hood, and then loading it into the model, doing the inference, and then coming back with the response when you call the generator. That is essentially what is going on, but as you can kind of see from the reference model, we've got a good explanation of what tokenization is and what the large language models are doing on the architecture. You've got this output layer, you've got this embeddings layer, which is really the bit that you're interacting with, and then the attention layers in between. And again, in future videos, I'm going to explain exactly what's going on in these layers as well. So hopefully this has got you really familiar with tokenization. It's got you familiar with what large language models are doing and what the HuggingFace transformer classes are. And it's important for us because as we start to build those models, if we want to be compatible with HuggingFace, then we're going to have to build or reuse tokenizers that are in that library, and same with the models, and understand what those model configs are and be able to understand how other people have been building their models. And again, when you start to look at people's papers, you will start to understand what all of these layers are doing. So anyway, I hope this has been a useful video. I hope it's given you a bit of an understanding of what's going on under the hood. And then as we drive through future videos, we're going to get more into the details of what's happening on each layers. And on that, I will catch you in the next video.